This video is talking about searching and sorting, and also including two-dimensional arrays. This is going to cover the broad topics of dealing with collections in Java, basic operations. Starting with linear searching. Searching is a common practice for lists. The most common search algorithm is a linear or sequential search. This means you start from one end of the list and look in order for the value. So let's take an example. Find the value 61 using a sequential search. So here we are starting at the beginning of the array, and we'll look through each index until we find 61. So we keep looking and looking until we find that at index 6, 61 exists. So that's fairly straightforward. Start at one. You can start at the other end and work back your way backwards, but essentially a linear search starts at one end and keeps looking until you find it. A binary search is usually more efficient than a linear search. We cover the reasons why it's efficient and when it's not efficient in a different video. The search assumes that all the values are in some sort of order. So you can see here in this example, they're all start from a low value and go to a high value. Now that we assume that there is an order to the values in the list, we search by splitting up the list into a lower and upper. So let's take the same question we had from the previous example. Let's find 61. So we split it in half, and we take a look at the value at the midpoint. The midpoint value is 43. Since 43 doesn't equal 61, then we have to take something we know about the array. We know that all the higher values are in the upper half of the array. So we're going to repeat the search, but we're going to use the upper portion of the array. So let's do that again. We split that portion in half, and we look at the value 79. We know that 61 is less than 79, so we're going to look below that array, which only leaves us 6 at the last point, and sure enough, we find 61 at the third time we search through that. So it's essentially a faster way to split up how to find a value in a sorted array. Sorting we're going to talk about sorting. Sorting arranges values in a list in a particular order. So the easiest way to talk about sorting is through numbers. Numbers already have a natural order to themselves. For example, low to high. We can see here that we can arrange numbers from lower values to higher values. They have some sort of intrinsic value to them. I can do the same thing backwards. I can start with high and work my way lower. But you can see that they naturally have some sort of order to themselves, where one goes in front of the other. Now, strings, one of the ways that we think of ordering strings is alphabetical order. We've heard of alphabetical order, where A's come before B's, come before C's, come before O's and T's. So you can see we've sorted this in alphabetical order, starting with apple and working our way to tomato. Now, we can define custom orders for custom objects. So in this case, I have a custom object called car, where I have name and cost. I'm going to create an order for cars by saying I want to order them lower to higher by how much they cost. And if two cars are equal to have the same cost, I will sort them by the name. So you can see right here, we start with the lowest value car, which is $15,000. The next value cars you see are 26. They're both $26,000. So the next, we know that they are in order because C comes before M. So even though that Camry and the Mustang are equal in cost, alphabetically Camry comes before Mustang. So that's a way I can take a custom object and define how different objects are in order in relationship to each other. Taking that one step further, that kind of goes back to what we were talking about in the previous chapter from comparable. Here I take, in our same example, I'm creating a car object, and I'm going to implement comparable. Here when I want to define how each car compares to another, I override the compare to. I'm going to pass in another car object, and I compare the cost of the two cars. I can say this cost versus the other cost. If the cost isn't equal, that means one car's cost is greater than the other, I'm just going to return that value. However, if the cost is the same, I'm going to compare the names alphabetically. I'm going to compare one name to the other name. So that's how I could do my custom ordering, where I look at two values rather than just one, and say one car is in order compared to another car by overriding the compare to feature. That's one reason why we would use the comparable object, is to be able to sort objects. Now we can talk about efficiency of algorithms, both search and sorting algorithms. Algorithms are classified on how efficient they are. There are two different key classifications: time efficiency and space efficiency. Time efficiency is how fast an algorithm can do its job. If an algorithm is super fast, then it's more efficient than an algorithm that takes a long time to do. Another way we can calculate efficiency of algorithms is space efficiency. How much space does an algorithm take? If I have to make copies of arrays in order to do my algorithm, I'm taking up a lot of space. So if I can do all my swapping and sorting in the same array, I'm being as efficient as I can by only using one chunk of memory. If I when I do my sorting algorithm, copy over to another array, I'm taking up twice as much space. So that would be less efficient space-wise. Now, we won't get into a lot of detail in this section, but the way that computer scientists calculate efficiencies is using what we call a big O notation. We won't fully cover it, but this section will kind of give you an idea of what we're talking about. Essentially, think of n as the unknown number of items that are passed to an algorithm. So if I have an array of 1,000,000 items, substitute 1,000,000 for n. How many times do I have to do the algorithm? The simplest algorithm is O of n. So that depicts an algorithm that goes through the number of items once. So here you see an array of arguments. Now if I have an array of 5 arguments, I'm going to loop through this 5 times, or n times. If this has 1,000,000 arguments, I'm going to loop through it 1,000,000 times. So that n holds the number of values the number of times I'm going to iterate through this algorithm. That's fairly straightforward, just straight up O of n. So think about this O of 2n. An O of 2n is an algorithm that goes through the number of items twice. So here you can see I've looped through it once, and then after that loop I loop through it again. So think of it, I loop through it n times, and then I loop through it n times. So I loop through it 2 times n. So 1, 2, 2n. So if I loop through it a third time, it would be 3n, because I'm doing it 3 times. So in essence, you can see that the number of items is args. So if I loop through it 1,000,000 times, so I'm looking through this 1,000,000, and this is 2,000,000 times. So 2 times 1,000,000 is 2,000,000. If it's 10, I loop through it 10, 20. If I do this 3 times, it'll be 10, 20, 30. The number of times I would have to multiply 2 times that number. N squared is an algorithm for each item in the list that I loop through I evaluate all the items in that list. So think about this as a loop within a loop. Here we have a loop where I loop through the number of items in the array, and then inside that loop I loop through that again. So where I'm mashing all the different arguments against all the other arguments in that list. So if I had 10 arguments in a list, I go through this 10 times, and then for each 10 times I loop through it another 10 times. So it's 10 times 10, which would be 100 times. So I'd have to do this 100 times. Do this 10 times, go to the next list, do this 10 times, go to the next list 10 times. So if I was to figure out how many times I would execute this algorithm here, it would be n times n, or n squared. Selection and insertion sorts have similar type of efficiencies. Both of them loop through the list and then compare each element with other elements in a list. This is a loop in a loop, or O of n squared efficiency. So both selection and insertion sorts, you can see, have a loop and then another loop inside that loop. So we say that selection and insertion sorts are O of n squared, which is fairly inefficient. Now, if you wanted to see which is efficient, an O of n operation is more efficient than an O of 2n operation, which is more efficient than an O of n squared operation. We'll get into other types of algorithms later on as we go into other sorts in different chapters. Moving along, we're talking about two-dimensional arrays. We've said that arrays can store primitives and objects. However, arrays are objects. This leads to the concept of an array of arrays, or a two-dimensional array. So here's a one-dimensional array, here's a two-dimensional array. So you can say we have an array of arrays. Think of it like a table of rows and columns. So we have one array. The first array is an array, the second array, and so on. To create a two-dimensional array, you specify each dimension separately. Here's an example of a 5 by 10 two-dimensional array. To reference the location in the array, you use both indexes. So if we take a look here, I create a two-dimensional array of strings. This is how I depict it in my code. I say I'm going to create a two-dimensional array of strings called array 2D color, and then I create it with 5 rows and 10 columns. So here I have an array of 5 rows and 10 columns. Here I'm going to set the position of 0, 3 to blue. Here I set position 2, row 2, column 4 to green. Here I'm going to print out that color. Now, this is an array of arrays. So if I wanted to grab specifically a row, I would grab row 2. Well, actually, this is row 3 because it starts 0, 1, 2. But you can see that I'm grabbing row 3 and creating a single dimension array of values. So I like working with pictures, so let's try and look at that as far as pictures are concerned. So let's start off. The first line creates my two-dimensional array of 5 rows and 10 columns. So I create a new string of 5 rows and 10 columns. I'm going to set position 0, 3 to blue. So here I can see row 0, column 3 is now blue. Now I'm going to set position 2, 4 to green. Now I'm going to grab row 2. So here I am, I'm going to grab row 2. And now I have this array, 0, 1, 2, 3, 4, as a single dimension array. Finally, we're going to get to array lists. Now that we've dealt with Java arrays being static, we're going to get into the array list. An array list is a collection object that Java provides that functions just like an array. Now, array list is just a collection of objects, anything that inherits from Java Lang object. This means it does not hold primitives like int or double, so you can't have an array list of int. You can have an array list of integer or double because those are objects, so you can wrap your primitives into integers or doubles. So let's take a look at some code. The really cool thing about array lists is that they can dynamically grow and shrink. The key feature of this is that I don't have to specify how big the array list when I create it. It's just there. As I add new values to the list, here I am adding my car example. I'm adding a new Mustang, I'm adding a new Ferrari, I'm adding a new Camry. I can get it dynamically expands to cover however many items I add. Now I'm adding this to the end of the array. I don't have to specify where I'm adding this to, and I can automatically grab it as long as it's within that, as long as I've created that many cars. Now here, another really cool feature is that I can insert in the middle of the array. So here, even though I have 3, I have 0, 1, 2, I'm going to add a Tesla right in the middle, right before Camry. So this list will shift Camry down, and then I'll have a Mustang, Ferrari, a Tesla, then a Camry. So it automatically shifts and inserts values without having to mess around with moving things. Also, you can see right here, I'm removing the second item. I'm removing Ferrari. So everything will shift back down. It also has a function called size to tell me how big this is. All that custom stuff that we kept track of in our labs, Java already does that with the array list. It already takes care of all this item. Last thing you notice here is that it's using Java generics. An array list, you have to specify what object type you have a list of. And in this case, I'm making an array list of cars. So you can see I have a list of cars. So I can't do strings here. I can't put a string here because it's in a list of cars, not strings. That concludes this video of searching and sorting, and also two-dimensional arrays.